Okay, so for lesson 9, what we're looking at first is whether or not something is equivalent or not. And so for equivalence, we need to know what the definition is because it's not the same as being equal. So something being equal would be exact numbers of things, okay, like one apple to one apple, or 4 chairs and 4 chairs, okay. For equivalent, what they're basically saying is that we could have 2 plus 2 equals 4. Okay, so the 2 plus 2 and the 4 are equivalent, right? They mean the same thing, but they aren't exactly equal. Another one would be feet and inches, right? It takes 12 inches to make a foot. And so those are equivalent. They are not equal. Okay, so it's kind of important to understand that definition first. So the first thing we should do here is set up a table, and we can look at this directly. So first we're going to have x, right? We're going to have our number x, and then we're going to look at x squared, right? And then the other one that they're asking about is 2 to the x. Okay, so let's go ahead and write down some numbers here. Okay, so now when we take each of these numbers and square them, okay, we're going to get the following numbers. Okay, and now when we take 2 and we raise it to the power of x, we're going to have these values. Okay, so are the two expressions equivalent? Well, no. We can see that they do have a couple places where they're equal, right? Like they are equal here, and they are equal here, right? But they are not equal anywhere else, so no. Basically, this is just going to be, we could agree with Diego. Okay, and so that's kind of like the best way to do that. All right, let's look at the next one for 9.2. Okay, for this problem, let me just go ahead and zoom in a little bit. All right, so important to understand what the graph is telling us, right? So it looks like the cost in dollars to produce 1 watt of solar energy is a function of the number of years since 1977. Okay, so when we look at the graph down here, we know that this is 1977, right? And then these are going to be our years since. So I don't like it to have all these empty lines, so I'm just going to put a few more in here. Might make our lives a little bit easier. Okay, and then over here, same thing for that 10. We'll do 30. Let's do 50 and 70. Okay, so from 1977 to 1987, the cost could be modeled by an exponential function. Here is the graph. Okay, so what is the statement? F of 9 is approximately 6 saying about the situation. Okay, so F of 9, okay, so this is going to be 9 years, right, since 1977. It is approximately, if we look, probably around 6. Okay, and so what this means is 9 years after 1977, right, that would be 1986. Cost in dollars 1 watt of solar energy is about $6. Okay, and so the next ones, what about f of 4 and f of 3.5? Okay, so we're going to find those pretty much the same way. Okay, so let me get that down here for you. Okay, so f of 4 is approximately 25 and f of 3.5 is approximately 30. These values represent the cost in dollars of 1 watt of solar energy, okay, in 1981, 4 years after 1977, and halfway through 1980, 3.5 years after 1977. Okay. When f of 4, when f of t equals 45, what is t? Okay, so let's go ahead and pop that in there for you. Okay, so for this one, 2 years after 1977 or 1979, the cost in dollars of 1 watt of solar energy was $45. Okay, and then the next one, we can make a table. I think that might be a good idea. So give me a second to get that table. Okay, so I created a table here. Basically, we're just looking at how much change there is. And so we can see that it's about 0.76 between 25 and 19, between 19 and 14.73. The book says that the difference is 3/4 or 0.75. So I guess I'll go ahead and put that over here as well. Because what I pulled from the table are basically just estimates. Okay, let's look at the next one. So the thickness in millimeters of a folded sheet of paper after it is folded n times is given by the equation T equals 0.05 times 2 to the nth. So what does the number 0.05 represent in this situation? Okay, so 0.05, that is going to represent that the sheet of paper is 0.05 millimeters thick. Okay, now it says use graphing technology to graph the equation T equals 0.05 times 2 to the nth. Okay, so I put over here a table that is going to show us the values of t between 0 and 5. Okay, so n is being the number of folds and t being the thickness. We know that when the paper is flat and there's no folds, the thickness is 0.05 millimeters. Okay, and then we're just going to plug the values of n in to get our t. Over here on the right hand side is what the graph would look like. Okay, and so it's asking how many folds does it take before the folded sheet of paper is more than 1 millimeter thick. Okay, and then how many folds before it is more than that. So one of the things that is important to remember, right, is what our axes are. Okay, and so down here we have the number of folds our independent variable. Our dependent variable is the thickness. Okay, and so we can see here, right here, our number of folds, okay, at 4, right, is less than 1 millimeter. Okay, at 5, it's more than that. Okay, and so it takes 5 folds before the paper is more than 1 millimeter thick. Okay, after 4 folds, right, it is about 0.8 millimeters thick. Okay, so that's what the table and the graph are telling us. I'm going to go ahead and just put over here what the text says. There we go. So it takes 5 folds before the paper is more than 1 millimeter thick. After 4 folds, the paper is 0.8 millimeters thick. And after 5 fold is 1.6. It takes 8 folds before the paper is more than 1 centimeter or 10 millimeters thick. Okay, or 1.28 to be precise. Okay, and so when you're looking at the graph in Desmos or GeoGebra, you can actually extend this and see those points. Okay, let's look at the next one. The area of a sheet of paper is 93.5 square inches. Find the remaining visible area of the sheet of paper after it is folded in half once, twice, and 3 times. So for this one, we're just going to take our value of 93.5, okay, and we're going to divide it by 2. Okay, and that will give us 46.75. Okay, then we're going to do the same thing with this one. We're going to take 46.75 and we'll divide it by 2. Okay, and then that's going to give us 23.375. And then we'll do the same thing here. We'll take our 23.375 and divide by 2. And this will give us 11.6875. Okay, and so that's going to be the remaining visible area. Okay, so what would our expression look like here? Okay, so what we're going to have is A is the visible area is equal to our initial area, right, times how much things change and how many times we're folding it. How much it changes and how many times. Okay, so let's go ahead and graph that equation. Okay, so over here we have our graph, and it is asking us can n take negative values? Okay, and so no, unless you unfold the paper. Okay, so can it take negative values? Not unless you are unfolding. And then remember A tells us the area, so can it be negative? No. Okay, it can never be, the area can never be made negative. Let's look at the next one. Let's go ahead and look at the, are you ready for more? Okay, so what I did here is basically brought down the formula, and I said that found out that in 1 meter there's 1,000 millimeters, and then in 1 kilometer there are 1.0 times 10 to the 6th millimeters. Okay, and I did that because our thickness is in millimeters. Okay, so I went on to Desmos and plugged in some values of n until I found out how many times it would be folded. Okay, so for 1 meter, it's going to be 15 times. Okay, and for 1 kilometer, you need to fold it 15 times. Okay, we will skip the number 4. Okay, and then remember to always read through the summary.